Hello. Good afternoon, everyone, and welcome to another session of Asset Colloquium. Today, we have a very nice and technical presentation, and one of our own, Dr. Srinivasan here, is going to present a talk on recent research activities at low temperature facility, as he is in charge of the scientist in charge of the facility there. And of course, along with some of his students, he has been guiding in internship. They mentioned they will be co-presenting with him. So he will give an overview of the work which has been done and the technical aspects of the thing they will be explaining in detail. The co-presenters, which of course he will introduce to you. And of course, Dr. Srinivasan doesn't need an introduction to TIFR people here, but I will just formally say that he has finished his BE in mechanical and then ME master's and his doctorate PhD in cryogenics. And he's been working in TIFR for almost 25 years, more than that. And he's been doing a lot of work in our low temperature facility, as you are available here. And he has been serving in a lot of, as a consultant and in administration board of a lot of IITs and others where this kind of low temperature cryogenic facilities are being set up under his guidance and with his correspondences and things like that. And I welcome him to give a presentation.
Thank you very much, Parag, for an introduction, and thank you very much for giving me an opportunity to present in this very prestigious forum, that too for the fifth time in my career. So this is my fifth asset. So this is a bit a collection of two groups thing, and I would introduce the two groups. The first group is from the Sardar Patel College of Engineering, Andheri, Mr. Woodrow, and Mr. Saiesh and Ms. Srushti, hello. So they are in the sixth semester of BTech in telecommunication and electronics and telecommunication. And other go is that from Ms. Abirami Sivakumar. She's from University of Waterloo, Canada. And she's doing a fourth semester in Bachelor of Applied Science in biomedical engineering from I think. So these people going to give two project topics. Okay. And just wanted to mention you that these people are internship people, students who are working for last about 4 months. Okay. So what they are going to present here is about 4 months work. So you know that it's a very, very short period, and we know how difficult to go to present a work after learning, because even 1 month of initial period will go in to understand what is what, and because there are many of the pre-project has to be studied, literature survey has to happen, move with the people, understand the project, and then start doing. So basically it's about 3 months, and then come to this stage is a quite challenging both for them as well as for me to bring this up. Now, when this project was taken, that this a common point is our liquid nitrogen plant at LTF. This is a Stirling cycle based liquid nitrogen plant. And basically, it works with a Stirling cycle, which produces like refrigeration effect. So the basic process I will explain without spending much time in that. The atmospheric air is taken, it compressed in a compressor, and it gets purified with various type of filters. Then it passed to another set of filter where from the air, oxygen and nitrogens are separated. So the nitrogen gas after separation goes to this cryocooler. It's like a condensing area. So it's just like a refrigerator, what you call a cryo refrigerator. The nitrogen gas goes there. The temperature is cold enough that it gets condensed, so that we get the liquid nitrogen goes stored here. Now, during the separation of air from nitrogen and oxygen, the left out gas is an oxygen. So which is thrown into air, which is like a waste gas. So the project is that to capture this waste gas, which is oxygen-rich air, and try to have a high-quality medical-grade oxygen from that without disturbing this plant operation. So the plant will continue to produce liquid nitrogen. Whatever the waste gas is taken out, do the process, and then we'll get the medical-grade oxygen. Okay, that was one project. So that in that project is we have taken up during COVID time. Then we applied for a SERB-funded project, which is what now happening, on which there are many parameters are monitored during the process of oxygen separation. To monitor those parameters, we have to develop an automation, a graphical process visualization screen, That is what the students are going to present as the first part of it. The second part of it is coupled to the cryo refrigerator. That the other part is at warm gas. When the gas enters, it gets condensed. So there is some cycle of operation like a normal refrigeration. There is some operation takes place. And during the operation, the cold is produced. And I'm going to explain the further slide. And one of the critical component, what you call as a regenerator, is a heart of this entire cycle. So the project is to have an indigenous development of cryogenerator or regenerator. And this has been taken up few years back. And in continuation to that, we have to optimize the regenerator for further performance enhancement. And the current second project would be to the simulation study of this new concept of regenerator, which is what she is going to present. So both are, its common point is this one. One is on the warm side, other one is on the cold side. Now, to make you more convenient to understand, the nitrogen plant operation is something like this. We have a compressor where that air gets, atmospheric air compressed, then it's purified basically to remove the moisture, hydrocarbon and carbon dioxide. Then it passes to the gas separation where it gets separated into oxygen and nitrogen, and the nitrogen gas is collected and then get liquefied in this liquid nitrogen plant. Now here, the PSA, what is the PSA is like a pressure swing adsorption system. So the one system will be used, other will be in regeneration mode. I will explain in the next slide. So this PSA exhaust, that the waste gas is thrown into atmosphere, which is what our point of study here. Now, when we are doing this PSA separation or the separation of oxygen, nitrogen, which is a very standard technique. Now, if the absorbent, it is based on the absorbent selection. If the absorbent is carbon molecular sieve, it has a capacity to absorb nitrogen and release only oxygen. So, if this carbon molecular sieve is filled in this tank, when you pass the air through it, all the oxygen get trapped into the absorbent and the nitrogen goes out as a product gas, which is what liquefied. Now, if I change this adsorbent to zeolite, the zeolite has a capability to absorb nitrogen and release only oxygen. So, if you by changing this absorbent, the current plant can be converted into liquid, oxygen producing plant or the nitrogen producing plant. But it is only one at a time, not both. So it can work as either nitrogen production or oxygen production. Whereas this object is that without disturbing this CMS or this nitrogen producing, how do we get out the oxygen? So that is what the whole challenge is there. So the attempt is to recover oxygen-rich gas without disturbing this liquid nitrogen production. So that's the main catch point in the whole project. How do we go about? As a basic methodology, the gas what we get from the PSA exhaust, oxygen-rich air, it gets condensed in a condenser. For condensing, we use the liquid nitrogen produced from this flame plant. When the liquid condenses, it becomes a liquid air, oxygen-rich base, and it goes to our cryogenic distillation based on the boiling point, get distilled, and we throw out all the nitrogen, and we get a high purity oxygen. Whereas the actual process has a lot of components. As a pre-cooler, condenser, distillation column, recondenser. So many components are there. We need to monitor various parameters like mass flow, pressure, temperature, level sensor, purity. These are all need to be monitored to have the process optimization so that you achieve the high purity or a medical grade oxygen. So this talk will describe, the first portion of the talk will describe about the development of process visualization screen in LabVIEW, which come monitoring tool and also the data logging tool. So that is what they are going to present in the first part. So the preamp is that it is part of this project. Only the development of screen, the automation part is the process of presentation today. And this typically to show the density of the work, where we get the oxygen-rich air. So you have to measure various values. Then it goes to a condenser that is filled with the liquid nitrogen, get condensed, and then go to a distillation column where it get distilled, where we get the high purity oxygen which get collected in this tank. Whenever to optimize the process, whatever the cold vapor because of the hot air coming in, we have to reutilize using the pre-cooling so that the usage of liquid nitrogen is reduced. So the gas going in, it get pre-cooled with the vent gas, which is anyway thrown out. Now, coming to the second part of it, the first portion is what we have up to here. Now we are going into this cryogenerator part, where it is like, I'm not going into the cycle of this operation. This works on the Stirling, reversed Stirling cycle based thing, where it's like a working medium, which is usually helium gas. The helium gas is subjected to compression and expansion process. So that compression leads to some increase in temperature and expansion leads to reduction in temperature. So it's in a closed cycle. It goes out in a kind of an synchronized manner in such a way that the gas is continuously compressed and then it is continuously expanded. So this portion, it gets cold over a cycle because this runs in a very high frequency from 36 hertz to 50 hertz. So in a revolution of crankshaft. So these are all the components. You have a piston. So when the gas gets compressed, it gets cooled with a cooler. Then it passes through the regenerator, which is of our interest. Then goes to here and then get expanded. So when the nitrogen gas comes here, it gets condensed. And during this, so these components is part of the cycle. But no. Okay, so now regenerator is nothing but it is an heat exchanger. So normally there are two types of heat exchanger: recuperative heat exchanger and regenerative heat exchanger. This is a regenerative heat exchanger where the gas can either go in one direction and the same time it's not going to come out in the same time. So next cycle it come back in the reverse direction, the same path. So it is a heart of this plant. The performance of this part component will decide the performance of the cryo refrigerator or the cryo cooler. The performance and the design is highly complex because it's a patented. If we have a plant which is the design is of 1950s, because nobody could come up with much better component which can use for a commercial and large capacity plants. Okay, so it's a bit complex, the design of it. This is what we wanted to work to make it more emphasis of it. When the cycle operates in a high frequency, the temperature of this expansion space keeps coming out. So what we are interested is the regenerator is here inlet and this is an outlet. So I will show the next component. So the outlet of the regenerator, the gas gets keep going down and down. So if you see at the compression space, the temperature increases, cooler it brought back, and the regenerator and the expansion space. So not much thing. The point what I would like to mention is, if you see here, the temperature at the inlet is same, and the temperature at the outlet of the regenerator keep coming down to a saturation temperature by which it goes up to 65 to 50 K, depending upon the gas and then operating pressure. It has a large value and about the frequency of it. So the typical regenerator efficiency should be something you have to design up 99.7%, which is the actual value. So designing a regenerator or a heat exchanger of this such high effectiveness is very, very difficult. So, and that too, the regenerator component is about 40 mm height. And you see the one side is 300 K and the other is about 50 K. So there's a huge temperature gradient. So it also gives an idea that how critical the component is. And the actual regenerator which is used in the existing plant, whatever the patented version, is of many such layers. It is a woven wire mesh. It's not a net, it's a woven wire mesh. So many such layers are stacked to form a shape. And this is about 50 mm. This is the height of it, 49 mm. And it's about 100 mm diameter. So it's such a small portion. And then this inlet is 300. Here you can go down to 50 K or so. So this is an actual SEM photograph of an thing. Is about 30 micron thing. So now, what we did, which is part of our previous project, is that to develop this component, after the detailed study in a kind of developing a BCC lattice structure and of same amount porosity in other packing density was kept constant, and the whole based on the CAD modeling, we made a three-dimensional printing as additive manufacturing to get the proper. So in fact, this was the first component ever made in cryogenics. To reach the cryogenics one shot. So there may be component which may need something more to give it. So it is a single ready to use component which can go to cryogenics. This was the one of the thing, and we have a much referred paper. And then this is what I gave my asset in the last 2019. And this current project, of course, after this, we have made many changes in the lattice structure and another component. But what we are going to focus in the second part is that change a bit of porous structure in the lattice component and the structure. And we also to have a more contact of the gas with the matrix, what you call as a metal part, it's get improved by adding some baffles. So the current exercise, what we are doing is to add some baffles to this, in addition to this porous structure, and to make a material and try to study the fluid dynamics so that the output of this study would go for directly the additive manufacturing. So when you do that, a lot of things has to be checked whether whatever we do, whether it can be possible to print or not. So that we need to check. So that is what the second project. So this is actually the preamp to this whole project. Now I will ask this first group to present their work regarding this oxygen separation, automation and the oxygen separation. Please.
So good evening, everybody. I am Woodrow Gonsalves along with Saiesh Vandkar and Srushti Hallur. And we're going to be talking about the addition that we've done to the liquid nitrogen plant. Majorly, it is a data acquisition system based on LabVIEW. And what I mean by data acquisition here is to digitize the analog signal, to sample it and to store it. So that is as far as my definition of data acquisition goes for this project. I would now like to call upon Saiesh to take us through the objectives.
So in the beginning of the project, Sir described or briefed us on some of the objectives, like what he wants at the end, how should the end product look like. So coming to the objective, the first objective was to have a process visualization, by which I mean is that whenever a layman sees the main screen of the LabVIEW, he or she should be able to know what is going in the plant, or what are the processes required to get the pure oxygen at the end. And by looking at the screen, you will be able to know that if the plant is working correctly or not. So as many of you know, and those who don't know, currently at LTF, we have a nitrogen plant, a helium plant, and now we will have an oxygen plant. So it is very tedious to go everywhere, to log every data of every parameter periodically. So to tackle this problem, and this brings us to the second objective, which is the main objective of the whole project, is to provide accurate data display on one screen. So it will help by reducing the manual interference, and it will log the data automatically into the system, and the data will be stored periodically. So, and the third objective was to display the system parameters on the local process indication. Here you can see we have written local process indication, which means that along with the automatic data logging system, it is required or essential to have a local process indication, which benefits in a way that such that if the software gets corrupted or stops by any mean, we will have a local display of the parameters, which will help in avoiding any anomaly. And in the fourth point, you can see there are 3 subpoints, which will be later explained in the further presentation. So now me and Woodrow would take you to the hardware aspect of this whole project. And as I say hardware, you should be very careful while what you choose to run that hardware system. You should choose the devices and instruments according to your requirements and adhering the specificity. We have chosen these 5 sensors. This first is temperature sensor, second is pressure sensor, third is oxygen purity, fourth is mass flow meter, and the fifth one is liquid nitrogen level sensor. And you can see in these 3, there is a local indication of the values, but these temperature pressure sensor doesn't has any. So to tackle this problem, we chose this process indicator of select. Now there is a particular reason that we chose this peculiar process indicator. So Woodrow will further explain you what is the reason. Now I will come to the main component or the heart of our system, which is the PCI 1805 card, which is the data acquisition card, which helps in getting converting all the field data into digitizing all the field data and sending it to the computer. And now you will have a question that how can we connect this PCI and gather all the field information. So this is a terminal block of Adam 3962, which is like a mediator between the field signals and the computer. The terminal block is connected to the PCI using a female connectors. So now I would call Woodrow to further emphasize on the hardware part.
So the liquid oxygen plant is divided into 5 parts, and each of the part plays its important role in terms of the monitor parameters that have to be monitored. So this slide is supposed to give you a visual representation of the system that we've built. So it starts with this sensor. It's connected to the process indicator, which you can see locally. Then the output of this process indicator in terms of its retransmission output then goes into the terminal block, and via the DB62 cable, it is attached to a PCI card, which is fitted into the CPU. Further, it then takes over into LabVIEW, and the processing happens ahead. To talk about the connection diagram, the transmitter is working in a 2-wire mode. So what I mean by a 2-wire mode is that you're powering the sensor and you're getting the signal only using 2 wires. So how am I doing that? Is by using the 24-volt onboard DC supply of the process indicator itself. Now to measure the output, which is in the form of a 4 to 20 milliamp current loop, that would be on the input side. It's being measured by the onboard milliammeter of the process indicator. And parallelly, you have an isolated output. So the reason for taking this output is because if you add both of it in series, then it's a problem. So there is an isolated output in proportion with the input loop. So this output produces current in proportion with the input current. So the output current goes into the data acquisition card. It's being digitized and it's further being displayed. This is the schematic which Sir has discussed before. The idea of putting this is to show you at what level the parameters are being monitored. So in totality, there are 14 parameters around your screen, out of which 8 are temperature sensor, 2 are pressure, 2 are oxygen purity, 1 at the inlet and 1 at the outlet, and a liquid nitrogen level sensor, which tells you the amount of liquid nitrogen. Now, that was all about the hardware part and all that you needed to know about the hardware. Now, to guide you through the software part, Srushti would take over. Srushti.
Good afternoon, one and all. I would like to introduce with the software part of our project that we implemented using LabVIEW. So what is LabVIEW? LabVIEW stands for Laboratory Virtual Instrument Engineering Workbench. Unlike other traditional programming languages, LabVIEW has these graphical blocks known as virtual instruments or VIs that are used to design control system or automate the measurements, and we can visualize the data efficiently or also create applications. LabVIEW was developed by, so it is a graphical visual programming environment that was developed by National Instruments. On this particular slide, we can see there are 2 images. This is the front panel. That is the main user interface of the LabVIEW. And the second one is the block diagram, along with its VIs that are the graphical blocks. Using these VIs, we implement the logic behind what we see on the front panel. We build the code on the block diagram. We are using LabVIEW because it is feasible to view data in real time on LabVIEW. Further, I have included certain major codes that we have developed throughout the project. First, I will go through the database part. So what is database? It is very important because all the data that is coming from the sensors is getting appended at one location, that is Google spreadsheet in our project. Yes, we are using Google Cloud over here. So we have integrated the Python script in the LabVIEW. You can see over here, code location. Okay. So we have integrated the Python script in LabVIEW using the Python node. And in that Python script, we have also included the JSON key from the Google Cloud Service account that allows or grants us the access to Google Sheets and Drive API. So this JSON key, that is JavaScript object notation file, helps us to authenticate and write into the Google spreadsheet. So the one benefit of this Google spreadsheet is that the data is stored over there permanently, and we can view the data anytime for analyzing for the future use as well. Similar to it, we have also developed the logging of data on Excel as well. But certain blocks that were used over here are different. We use string blocks or reporting blocks in LabVIEW over here. The only benefit of both of them is that we can view this from like anywhere we are. We can view them at any place. Moving on further, oh, this is really crucial part of our slide that is alarm. So what is alarm? I'll explain you first with that. You can see over here, there is one parameter as an example that we have taken, and there are two comparison blocks over here. If this temperature parameter goes above this high or is below this low, say 50 degrees or minus 200, that we are manually setting up, then there will be an alarm that will be triggered. This alarm will be sent to the users of our facility, that is LTF, through this email code. And any an action will be taken, or any risk or hazardous situation will be prevented in future. Further, this is the LabVIEW main screen that we have developed by taking into account the schematic that was shown in the previous slide. This was done using the DSE module in LabVIEW. Now I would like to hand upon to Saiesh to display the video of our project.
So just a disclaimer to all of you that we have checked all the parameters and all the parameters are working, but due to some technical issues, we were not able to install the oxygen plant currently. So in some areas, some parameters will show garbage value allocated by the system. So kindly please ignore it. As you can see, there is a temperature sensor connected to the local process indicator, which is connected to terminal block, and via cable, the signal is going into the PCI card. And this is the main screen where you can see the temperature and the live reading of the oxygen purity as well. And Srinivasan sir wanted temperature converted to Kelvin. So this is the reading which is converted live. So these are the plots. This one specifically is of temperature. So as you notice the up and downs, but these are not the noise. As you can see, the scaling is went till 4 decimals. So 3 to 4 decimals. Now this graph is of the oxygen purity. Again, the scaling has went till 3 to 4 decimals. And now we will show the Google spreadsheet where you can see the live data, timestamp, and the date, month, year. Now as we start the process, Excel sheet is opened, and here again there is live data, timestamp, as well as the date, year. In alarm, if we have set a high, if it passes the threshold, see the alarm went off, and we got a mail. Now I would like to call Woodrow to summarize the results and outcomes and to present further.
So what have we done so far? What have we achieved? So as he mentioned, there was a disclaimer. The whole system hasn't been set up. It's been set up in different parts, and we are successful in testing each and every part. Finally, we've achieved a graphical user interface. And there has been a local process indication as well, along with simultaneous monitoring of the screen. And there's another important part that this work was recently submitted in the International Conference for Advances in Science and Technology, or as they call it, ICAST 2025. Future improvements to this work include SMS notification instead of email, which can be then received online. An email alert can be received online. And the distillation column still needs some sort of manual control, which is negligible, but it can be done further using LabVIEW, not just through our system. These are the references. Finally, I would like to thank our mentors for guiding us throughout this project, Dr. K.V. Srinivasan sir, Tulsiram sir, and Satyanarayan sir. The aim of the LTF staff is always to help us, and they have quite established that in helping us in our project continuously. Ms. Karande sir, who has helped us, and Avinash sir. Thank you for giving me this opportunity to present, and now I would like to call upon Abirami to continue the presentation.
Good afternoon. My name is Abirami Sivakumar, and today I'll be presenting to you our work on the computational analysis of a porous structured cryo-regenerator with baffles for additive manufacturing. So the objective of the work is to design and develop a high-performance regenerator for a Stirling cryocooler for nitrogen liquefaction by using additive manufacturing techniques. So we build upon the prior work done at LTF to build a stainless steel porous regenerator for the similar purposes. So shown here are the dimensional details of the previously modeled stainless steel or SS porous regenerator, which are also considered for the current study. So first we have the BCC or body structured cubic unit cell with the length of 1.9 millimeters and the strut diameter of 0.55 millimeters and a porosity of 66.39%. So it was selected based on the optimum porosity, surface area to volume ratio, and machinability for additive manufacturing. So the BCC structure was built based on the retrofit compatible dimensions for the regenerator, which is shown here. So in the current study, we take the same dimensional constraints, except we employ trapezoidal baffles throughout the SS porous structure, as shown here. So shown in this slide is the methodology that is taken for this study. So we begin with the Region 3.3 simulation software. So Region 3.3 is a free simulation software that is used specifically to optimize regenerators. So we begin with this in order to calculate some key input parameters to be used in the later steps of analysis, which is here, heat transfer coefficient and Reynolds number. So then we move on to the ANSYS Fluent Simulation software, in which we conduct computational fluid dynamics simulations, or CFD, in order to analyze the temperature, pressure, and velocity drops across the baffle type porous regenerator. So we target to have a higher temperature drop and a higher velocity drop, as well as a minimal pressure drop, in order to increase the efficiency of heat exchange and cooling throughout the regenerator. So we take these results and we initially compare them with the previous work which was done on the baffle-free SS porous regenerator. Then we take the results and we cross-verify them with results obtained from, again, Region 3.3. Then additionally, we conduct a stress analysis on the BCC structure on ANSYS Fluent software in order to identify the maximum von Mises stresses that develop throughout the porous structure when it is subject to the working pressure and temperature. So here we have a slide representing our current work, which is the trapezoidal baffle integrated regenerator. So we integrated trapezoidal baffles in order to increase the interaction time between the gas and the matrix, which would theoretically help us to obtain lower cold end temperatures via the regenerator. So these baffles were designed with some key objectives in mind. In order to, for example, increase the residence time between the gas and the matrix, 2,500 baffles were designed and modeled in 10 rows with linear high density packing and a 7-degree gap. And then additionally, in order to minimize the obstruction of the gas flow and minimize the pressure drop, the baffles were aligned crosswise with each other and positioned in the corners of the matrix. So now we move on to the first step, which is the Region 3.3 analysis. So the inputs for this analysis were chosen to closely model the actual inputs that can be found in the working conditions of the LTF plant. So for example, the working fluid was helium gas. The matrix material was stainless steel 316L. The pressure ratio was 1.25. The average pressure was 27 bar. And the inlet and outlet temperature was 30 and 300 Kelvin. And the other input parameters are tabulated here. So again, Region 3.3 was first used to calculate some critical input parameters to be used for the ANSYS analysis, which was to find the heat transfer coefficient and the Reynolds number, which are shown in this graph. After that, Region 3.3 was used to calculate the pressure drop, temperature drop, and velocity drop across the length of the regenerator in order to later cross-verify and validate the results that would be obtained from ANSYS. So these values were taken at the outlet of the regenerator and at the final cycle or the endpoint of the simulation runtime. Now we move on to the ANSYS flow analysis component. So for ANSYS, we considered a configuration with steady state flow with absolute velocity and pressure formulation. So let's begin with this table. First of all, shows the simulation inputs at each window of the ANSYS software. So for the mesh metric or element quality, we targeted it to have a high quality as possible, and we obtained an average of 0.74 with a maximum of 0.98. For the cell zone conditions, we defined the regenerator as a porous body, and in order to calculate these values, we first obtained some critical inputs from the CAD model directly, such as the volume of fluid flow and the area, the wetted area. And we used formulas established in the literature in order to calculate values such as the relative velocity resistance and the inertial resistance coefficient. Then, based on the Reynolds number from the region 3.3 analysis, which was lower than 2000, we selected a flow model that was laminar in order to represent laminar flow conditions. And we kept the energy model as on in order to account for heat transfer. And additionally, the heat flux at the walls was considered to be 0 for simplicity of analysis because it was considered to have no lateral heat passing. Now shown here are the outputs obtained from the ANSYS software. So again, we have the pressure, temperature, and velocity variation across the length of the regenerator, which was taken at the outlet. And here is the graph of the scaled residuals from ANSYS, which indicates that the errors converge to mostly acceptable limits after about 5,000 iterations, which indicates solution accuracy. Now we have the stress analysis component. So the stress analysis component involved applying the working pressure to the lattice structure in order to observe the maximum equivalent stresses that develop in different areas of the structure. So to do this, we first imported a single unit of the BCC unit cell into Fusion 360. We created a linear pattern and added walls at the edges, which was following the procedure that was established in similar literature, but for slightly varying dimensions. So then once we had this, we applied a pressure of 30 bar throughout the entire porous structure, and you can see the distribution of the pressure in this diagram. And in this diagram, you can see the distribution of the equivalent stresses that develop in different parts of the porous structure, which is the results of this analysis. So now we move on to the overall results, beginning with the flow analysis. So first, we compare the ANSYS results for the baffle type regenerator to the results from the previous work, which were also obtained from ANSYS. So you can see here that there's a significant improvement in the temperature and the velocity drop when comparing the baffle type regenerator to the SS porous regenerator. So there is an improvement from 104 to 246 Kelvin of a temperature drop, as well as an improvement from 1.7 to 2.17 meters per second in velocity drop. And this is an indication of improved heat exchange and cooling efficiency throughout the regenerator when the baffles are added. Then with the pressure drop, however, a slight increase can be observed. However, it is extremely minimal, only a 2 Pascal increase from the previous and 12.5 Pascals in total, which is almost negligible when looking at the working pressure, which is 3 megapascals. So it doesn't impact the efficiency of the regenerator. Then we compare the ANSYS results to region 3.3 to cross-validate, with the understanding that region 3.3 is a software that models pulsatile flow, which is more accurate to real cryocooler conditions, while ANSYS assumes steady-state unidirectional flow. So you can see that some trends are definitely matched as per region 3.3. For example, the temperature drop again is much higher for the baffle type regenerator when compared to the previous work, which is a 267.49 Kelvin compared to 104 Kelvin. And the pressure drop also shows a slight increase, which is expected because when adding the baffles, the gas gets slightly obstructed. But again, it's very minimal when compared to the 3 megapascal working pressure, so it won't make much of a difference. So these results are consistent on region 3.3, but the velocity drop, as you can see, is there's a slight discrepancy, as in it's lower than both results for the baffle type and the SS porous regenerator. So this may be due to the fact that region 3.3 has a pulsatile flow model, so comparison may not be applicable in all areas. However, it does give us a better idea of what the regenerator would actually look like in real working conditions due to the pulsatile flow model. And it can give us, by combining both the ANSYS and region 3.3 results, we can get a realistic range for these three parameters that can give us an idea of what the regenerator would truly behave like. Now, for the stress analysis, we compare the current lattice structure to a similar lattice structure tested in the literature, which had a slightly smaller strut diameter and a lower working pressure. So you can see here that the maximum 1 meter stress that developed in the current lattice structure is higher than in the similar literature. Specifically, it's about 3.4 megapascals compared to about 0.2 megapascals developed in the lattice structure. However, again, this is very minimal when looking at the yield stress of the material, which is SS316L and 460 megapascals. Despite this, it may still indicate that there is room for optimizing the design in order to prevent deformation and failure over time, as well as optimizing the working pressure. So here we have some further details on the results. So for ANSYS, about 25 iterations were conducted. The input parameters were varied from iteration to more closely model the cryogenerator conditions. And additionally, the meshing had to be refined and fine-tuned in order to have a higher element quality. And each iteration took about 2 hours on ANSYS to complete, and this was done over 4 months. Similarly, in region 3.3, 10 iterations were conducted roughly with varying input conditions in order to more closely represent the plant conditions. For example, conditions such as frequency and number of cycles were varied. And the current work has already been presented in an international conference, with the paper having currently been submitted to the Research Plateau Current Trends in Engineering and Technology journal, currently being under review. So this brings us to our discussion. In conclusion, the SS porous regenerator with baffles showed some significant improvements in the heat exchange and cooling efficiency, which was seen by the improvements in the temperature and velocity drop, as well as a minimal trade-off, almost negligible trade-off in the pressure drop. And these results were cross-validated by region 3.3. As for the stress analysis, the current lattice structure did show a slightly higher maximum von Mises stress than similar literature, but this is again completely acceptable because it is much lower than the yield stress of the material, but it may signify room for further optimization of the design. As for limitations, in the current study, the ANSYS student version was used. So the ANSYS student version comes with a limitation in the number of nodes and elements that can be employed, which may limit the solution accuracy and results accuracy. And furthermore, as previously mentioned, ANSYS was the main simulation software that was employed in the study, and ANSYS models steady state flow conditions, not transient or pulsating. So this may not give us the best idea of what the regenerator would behave like in real conditions, but it does allow us to compare to prior work, and we can still take it while acknowledging the region 3.3 outputs, which can give us a better idea overall. So as for future work, we hope to conduct analysis using the commercial ANSYS license, which will remove the limitations on the mesh size and element count and improve the accuracy of the solution. And currently, we are also working on the factor of safety simulation for our structural analysis component. So once we are able to better visualize how the factor of safety is distributed throughout the porous structure, we can better compare it to similar models and learn where to further optimize the design. And we also are aiming to conduct the analysis under varying operating pressures to see what kind of effect that has on the stresses that develop within the lattice structure and the temperature, pressure, and velocity profiles. So that brings us to the references, and we would like to acknowledge those that have helped us throughout this work, including in the CAD modeling and the simulation aspects. So Ms. Preeti Sai and Ms. Joyce from Anna University of Chennai, who were project students in charge of the previous work, Mr. Rahul Pokale, Mr. Rajesh Sharma, Mr. Avinash Shinde, and all the staff at LTF TIFR. Thank you.
Presentations and to the previous presenters as well, and Dr. Srinivasan. Yeah, sure. Please go.
Conclude that connecting part of these two talks is that the take home of this, the work of simulation study will go directly into this additive manufacturing, which we have been waiting as a part of an indigenous development. So we are very close to the result, and this results was very helpful in going ahead. So while doing so, that when many iterations are happening, it not only that what is the porous structure and the baffle to be done, it's also to be machinable. So we also need the input from the manufacturer whether this can be possible or not. Like in the previous study, what Preeti and Joyce did that. So that was we went for a porous structure with a modified lattice structure. Then we went to for further optimization. We went to hybrid mode. So the hybrid mode, which have an half of this length of 50 mm would be SS and remaining part would be lead. But that has an operational limitation in kind of a machinability. So the machine, the additive manufacturing, the layer by layer techniques will not possible to have change of material in middle of the operation, because the layer from SS to copper, that connectivity is a bit problematic. So people are not. In addition to that, when something has to happen in additive manufacturing, the additive manufacturing concept and porous structure is totally different. It cannot be possible. And this is the first time that even the vendor, when the last time when the porous structure was made. So this has a lot of implication in the kind of a fabrication. We wanted to go ahead further with that, this kind of a baffle, which become a single material and adding. So we wanted to go ahead with the further. So this is the main catch of the thing. As far as the oxygen separation process is there, we are almost ready, because many of the detail we couldn't check the actual process is because that unfortunately the nitrogen plant at TIFR got an breakdown since November. So we are ready with the process, but we couldn't test in full swing because of this issue. So many of the parameters, we have checked all the parameters, bits and pieces, not as a process altogether, which will be there. And second thing, the 4-month project, roughly about 5-month project is what is the time, and we have 1 month left for that, because these people are going to be here for another 1 month. Whereas Abirami would be, her time is finished. But she is also working in the simulation of the distillation column, CAD modeling, solid modeling and thermal simulation of column alone is working as a parallel within few days. So that is also part of the thing. So what I would say is, all said and done with a limited thing. And for the additive manufacturing, we have very, very limited comparison detail. So we have to go ahead with all the works we have done is so far with our own previous work. So catching a person and discussing with them who has completed the project 2018 is a bit thing. So we have a limited access to resources, and IPR also we contacted because of the commercial license, but it has an own problem. But all said and done, that end of the project, both these terms of oxygen separation here, it has come out very well, and I'm very happy in that, and I'm sure that you will also appreciate these young chaps who have done from 4 months of study and work to come to this platform of asset is something very, very difficult. I'm sure, and on behalf of me and for you, I take the liberty in congratulating all these chaps, young chaps, for a great future. Please come back. So I would allow some any questions is there they should answer. Any question?
Now it's open to questions if anybody.
Can you please go to the signal chain? Before this. Yes, before this.
Yes.
Yes, so from this local HMI to the terminal box, so is this signal analog or digital?
It's still analog. It's still analog.
This is analog.
It's still analog.
So this sensor and this local HMI side, this is remote. and this terminal block and digitization system, it is remote, so like
Yes.
far away. So do you think this analog signal is prone to noise if we digitize it just at the level of sensor and transfer the digital data instead? So will that be any better, you believe?
That was a very interesting question. I was expecting this. So the problem with that system is that we won't have any flexibility, or currently what we have to digitize at our end. So you won't be able to alter the sampling rates. You won't be able to have it parallelly. You're talking about a system that is digitized there itself, that will send itself the data in packets, which will go serially. This is happening all parallelly. I can access any parameter at any moment of time. I mean, given the fact that we already had this data acquisition card with us, we went ahead with this system. So
I missed it. All the instrumentation was already procured earlier because we had a practice of, we had used earlier that all the transmitter with 4 to 20 milliamps. In fact, all the instrumentation is the 4 to 20 milliamp. So they have to live with that. So, and the card and the other thing, because of the cost economics, we don't want to go for PLC, we went for this. So they were forced to do this per time only. And so this was the only option available because everything has 4 to 20 milliamps output.
Yeah, so I have another question. Yeah, so in the software part, so why are you using Google Sheets? Like, is there any particular reason? I just want to know. There are other options like MQTT, InfluxDB, those stuff. So is there any particular reason?
We actually tried to use SQLite before this, the database. For a week, I tried doing that, but it was not happening somehow.
Yeah, it's difficult to use.
Yeah, exactly.
Okay.
First of all, Google Cloud Console, it was for free, and there was this is cost effective, and the database got appended, like it got worked in a week itself. So we continued with it and did not try any other.
So for other like MQTT and those stuff, you also have like local hosting options instead of like Google, it is going some server. So if you want data protection and something, so this is also a good option. But okay, so yeah, Google things is much easier to use.
Yeah.
But for most of the proper IoT establishment, I have seen mostly they use this MQTT and other IoT optimized protocols.
Right.
Is any of your pressure or temperature sensors are coming in contact with the oxygen, because some oxygen rich environment may lead to some ignition? So is any care you are taken for that?
So I think Srinivasan sir, who has a more knowledge, can answer it.
The process is not yet ready. In fact, we have to optimize the parameter based on the input of what we get from this project. So probably, as I said, the distillation column, we need to achieve the temperature of liquid oxygen at the bottom. To maintain it, how to add the heat energy to the column, which will be done by the heating pads. So based on the various temperature, what we get, we have to adjust the heat flow. So we know we had with the pre-work, we had some base information, but this will give a complete idea of that how do we go. But the mapping of entire temperature profile across the column, which is the key point in achieving the oxygen purity. So which is yet to be done. Since the process is not ready, this project output will help us in going ahead with that. But right now, we don't know.
Okay, thank you.
Questions on the Zoom. So, yeah. So before I went to Zoom questions and things, I have a couple of questions for you guys. So thanks very much for a good presentation. One of the video slides which you showed, the sample rate looked like you are repeating your entire cycle of observation or acquisition of your parameters once every 3 seconds, or roughly that's the rate at which it was going. That's what I saw. So have you have some flexibility if some of the parameters are considered more critical to be sampled at higher rates? What is the software plan? Are you polling one at a time? You showed something like 20 parameters which you are acquiring throughout the cycle or throughout the plant. So have you thought about maybe pressure sensor data much more critically required to catch if there is any leak or any catastrophe which can give an alarm before it leads to a higher time? So
yeah, so there is a provision, like you can code in the backend of the LabVIEW. you can give a particular time to a particular parameter. So yeah, it is possible. But as far as so Srinivasan sir hasn't told us, so given the timing of every parameter, so we have not.
I mean, as a design engineers, you should have. Correct. So that is what the limiting has to be identified. What is the limiting
So
word?
initially for this tester, we had to do 3 seconds. In fact, eventually it will going to be every 1 minute. In fact, it should be 10 minutes. Whereas the data logging, the reporting will come every 1 hour reading of that period will come as a report by email. This is what we have been doing it. But right now, is any time is possible from 150 milliseconds to any second. So right now, it's just in a test mode that can be changed.
Satish, you may please unmute yourself and ask your question.
Thank you so much. My sincere and heartiest congratulations to Dr. Srinivasanji and the entire young team. Really a great job. I have 2 questions. Number 1, about the oxygen which you are tapping from the PSA. So at what pressure you are tapping, and then you are liquefying, condensing, and what is the output pressure, and whether it's a cost viable option, number 1. Second thing about regenerator, we are extremely excited that TIFR is really working since last couple of years to have this dream, to have an indigenous regenerator. I'm sure that this regenerator, which has been developed with a lot of baffles and all, it is interchangeable. But have we done any testing so far that whether it is really compatible or how much temperature 77K has been achieved or the liquefaction rate and all? If you can throw some light onto these 2 things, please.
I think this is best suited for sir.
Cost analysis, if you worked out.
Yeah. This analysis will be done in various operating pressure. As you know that the operating charging pressure of the helium in the cycle is 24, and then exit pressure, which goes in inlet pressure goes into the regenerator, can go up to 30 bar after the compression, and the frequency can also be changed. So it's a combination of permutation combination of all these frequency and pressure, with both are adjustable. So the optimization has to be done within these 2 parameters, considering that 1.2 gram per second is our mass flow, which is fixed. So some restriction, and all said and done, we need to have an outlet temperature, and the dimensional capacity of the regenerator has to be retrofit compatibility to the existing machine. So we have a limitation to operate parameters which we can play. So that is what we have done. And the previous work which we have done without baffles, it has gone up to 99K actual thing, which was measured in little a different way, not the expansion space. So there is a huge scope for improvement in that. And this is what that analysis helps us to go ahead further, because you know that SS316, the specific volumetric capacity ceases at around 30K or so. There's no more capacity to accept the refrigeration when the matrix material. So if it is 50 Kelvin is achieved, and then actual would be around 65K. So we have huge room for the error which can accommodate into the parameter. So it's a study, and we are hopeful that this work, because we have seen the lattice structure, printing, and the actual result. So we have much better control into the parameter optimization. So that's what we are planning. Ashish, is that fine? Okay, it's mute.
Once again, thank everybody for a wonderful lecture, and I wish you all the best. Thanks. Thanks. Correct.
Continuous help in
Guiding them into this right things.
So equal credit goes to Siram and
Yeah.
Because students were also trained to write the manuscript in a way, because a lot of changes in the IEEE template. So going back and forth, everything, and how do we, in fact, I'm sure that Satyanarayana would say that we have fulfilled your Izzat ka sawal matter. So when when we took a bold step for these people to go ahead with the asset tax, so he was bit worried. And after telling him, I myself was in a in a situation that whether we can fulfill or not. I'm sure. So I'm sure that Satyanarayana would agree with me.
Yeah, sure.
Yeah, Srinivasan, sorry, I was on mute, but really, thank you so much. Yes, I'm sure that with the consistent effort which you and your team is putting up, we are very near to the success. And as a director of Sterling India, whatever support which we can render, we are absolutely open and eager. Thank you so much.
Thanks.
and well
Thank you very
done.
much. Thanks, everybody. And I request everybody to join for a team outside the things. Satya, if you want to mention something?
Satya, are you online? Can unmute. Yeah, please. Yeah. We need your input, please.
Oh, okay. No. I'm listening very carefully, and really congratulations to all your collaborators, including those from my college, 3 of the boys and girls. And also, I mean, the way that you have put up in parallel both the hardware development as well as the simulations for your future work done by the other collaborators is very, I think, a great initiative. Yeah, so I can only congratulate you and congratulate your collaborators, and hopefully this will lead to further optimization of your system. And we are all waiting for your plan to come up so that their system gets tested.
Thank you very much.
Okay.
Thanks,
All the
everybody.
best.
We'll